Okay, so this is Introduction to Statistical Learning, Chapter 10, and we are on question 4, still in the conceptual questions here. So here's the several parts of the question. So we're considering a 32 by 32 grayscale image that has a convolution layer with 5 by 5 with 3 5 by 5 convolution filters, and also note that there's no boundary padding. In the first part, we're just going to draw a sketch of the input and first hidden layer, similar to a figure in the book, figure 10.8. You can go check that out. And this is what it looks like right here. Or I mean, this is me making an image, of course, but we have a 32 by 32 image. And then we have our little filter. Actually, we have a few filters, that are that are taking our image and then convoluting it. Is that the right use of that word? I'm not sure. But into 3 different intermediate layers here, and then presumably there might be continued layers, to the right of this that I don't think were intended to represent. So there's the answer. Also note that we go from 32 by 32 to 28 by 28 by virtue of our 5 by 5 filter. Okay, so that's a little bit of a mouthful. And so the question doesn't ask us about this, but I kind of put in a little bit of an explanation here. But roughly, if you imagine the filter, if you just go from left to right, and we'll just leave the up and down dimension alone, but if you go from left to right, so you put that leftmost edge of the filter on the leftmost edge of the image and slide it all the way over, then you will have 28 positions where the filter can be on top of the image. And again, this is all done without padding. So, if there was padding, you would have maybe a slightly larger convolution intermediate layer. But okay. So in part B, we're meant to answer how many parameters are in this model represented in the image here. Okay, well, we have 3 5 by 5 filters, and so those are creating our convolution layer. So we have 3 by 25 pixels, right? 5 by 5 is 25, and then there's also a bias term associated with each of, with our convolution filters. So for a total of 78 parameters. And then in parts, so there's 2 more parts here, C and D, and I just answer them together because they kind of fit together. But here's the question. So we're supposed to explain how the model can be thought of as an ordinary feed-forward neural network with individual pixels as inputs, but with constraints on the weights in the hidden units. And then what would the constraints be? And if there was no constraints, then how many weights would there be in an ordinary feed-forward model? Okay, so I guess I don't need that reminder to myself anymore since I'm making the video. Okay, so if we take the image, the 32 by 32 image, then we have 1,024 inputs, and it's being connected to 3 28 by 28 layers for a total of 2,352 elements in the hidden layer. And so if we had connections between each input and each hidden layer element, then we would have, roughly 124 times 2,352. But there's also bias terms, that we'd probably want to add for each, intercept terms or bias terms for each input element, leading to each, output element, for a total of 2.4 million parameters. Okay? But we already said that we only have 78 parameters. Okay, and so this isn't really a completely connected, or couldn't be really represented as a fully connected feed-forward neural network, because we have constraints. Right, so we're not fully connected between the 2 layers, and so because we have these constraints. And so what are the constraints? Well, the constraints are, the lack of connection between the layers, but that lack of connection is being instantiated by these filters that are only taking a subset of the inputs and mapping those to a subset of the, not really outputs, but the intermediate layer. Okay, we'll call that good.